Okay, so I'm continuing the filled acrylate discussion. This picture is a picture of their manufacturing process. So A is the same here, and I guess right here is a blue light emitter source. B was a image creator. C was like focusing lens, and then D was just a mirror to project it onto the build plate. And this is very similar to the clip process that we saw in a previous lecture. It was how they manufactured things. Okay, so the title of the research paper was A Miniature Flow Sensor Fabricated by Microstereolithography Employing a Magnetite Acrylic Nanocomposite Resin. It was produced in the UK, and the main focus of the paper was to use a magnetite-filled acrylic resin to make a flow sensor. So rather than having electrical wires and whatnot in your flow sensor, the material itself generates the electric field. So by adding the magnetite particles. And this picture on the right, so those are cubes they made with this composite resin, and that's a magnet holding them up. So the main question was, how does the filler affect the mechanical properties of the resin, and can it be used to design a flow sensor, especially a micro flow sensor? So their main approach was they used an EnvisionTech R11 resin that had a 1:2 ratio of monomer to crosslinker and 5 weight % of photoinitiator, and then they picked a 25 weight % of magnetite nanoparticles. They did say that if they went much beyond 25, that you would get a lot of scattering of light and you get really poor part quality, but they didn't show any data to back that up. And then they did compression tests on cubes, 5 millimeter cubes, and then they compressed them in the plane of the layers as well as perpendicular to the layers. And then they made this this flow rate here. The impeller was manufactured with this composite, and it had a 25 micron layer thickness, and they exposed it to 90-second bursts of the image. So rather than a laser moving back and forth, it's an image that they project per layer. And then the body of the flow sensor was just the unfilled R11, and it had a 25 micron layer thickness, but they only did a 30-second exposure of the light per layer. And then they used a mechanical tester and an AMR magnetic field sensor to measure the magnetic field produced by the magnetite resin. And one thing they also mentioned as far as filling the resin was, because magnetite naturally kind of clusters together due to magnetic fields, they had a higher viscosity resin so that the particles wouldn't clump together and you just have pockets of magnetite. So they tried to get more scattered, but they didn't. That was just kind of a footnote. They didn't really show any experimental process or data behind that. Okay, so the key result from the first study was mainly focusing at the mechanical effects that the magnetite filler has. So they did 2 compressive tests on both the unfilled resin and the filled resin. And the green corresponds to compression perpendicular to the layer thickness, so the layers are running in this direction, and red, it's in the same plane as the layer thickness. So as you can see, the green, you have a higher compressive strength, and in both cases, and for red you have lower, and you have a significantly lower compressive strength for the magnetite filled acrylic. So you do get a decrease in strength. And the main point was that the magnetite disrupts cross-linking, which leads to a lower strength value, and loading in the perpendicular plane is leading to a higher stress value. So while you may have a drop in strength, depending on how you load it, that could be mitigated. And then for the second study, they 3D printed this flow sensor. This is the assembled thing. This is some British coin. I don't know what size it is, but so they hooked it up to an air hose and with shop air, and they just ran different pressures through it. This Y scale is just an arbitrary number to show the relative magnitudes of magnetic field sensors, so there's no units on this side. But they did say, at a 3 psig, you get a higher amplitude or frequency, which means the impeller is spinning quicker, so you can correlate that to flow velocity. And they measure this with an offset sensor. So the AMR magnetic field sensor, you can just hold it up to the device and it would read it. And so they held it up at different ranges to see how far or how closely you need to be to the sensor. So the key point was an impeller rotational speed and therefore fluid velocity can be measured by sensing magnetic fields generated by a rotating impeller that has this composite material in it. So rather than having electricity run through it, or you're connecting and measuring a voltage or something like that, you can just measure this fluctuation of the magnetic field. Summary, the use of magnetite particles in a resin composite reduces strength, but it gives the magnetic properties that are desirable for micro machining and potentially MEMS technology. And devices such as this flow sensor are viable and made possible by what they were calling functional composites, and it's just materials that have more uses than just purely physical mechanical properties. So they didn't really report a standard deviation or show any evidence of multiple trials. It just kind of sounded like a one-off study. So that was a little bit disappointing, but it's a very innovative concept. I think you have a lot of potential, especially in the MEMS technology area.